researchers, and dear students. Today we gather to honor the memory of Professor Jagat Narayan Kapoor, a visionary mathematician and educator whose work continues to illuminate our understanding of science and society. His legacy reminds us that mathematics is not only a discipline of logic but also a language of truth and discovery. In his spirit, let us begin this lecture with gratitude for his contribution and inspiration from his life's work. So, the title of today's lecture is Structural Analysis of Ramanujan's Prime Number Theory Numbers with Digital Transformation and Modular Arithmetic. Ramanujan primes form an important class related to prime numbers. Their analytic properties are well understood, but their structural and digit-based behavior remains largely unexplored. So, the procedure which I am adopting to know the structural behavior of Ramanujan prime, it is sum of the squares of digits, which shortly we call as SST, and modular arithmetic, modular 6 and modular 9. There is hidden and try to identify hidden structural patterns and irregularities. Actually, my field is functional analysis and operator theory. When I was asked to give this memorial lecture, then in the last 2 months I wrote this and tried to find out some structural pattern in Ramanujan primes. So in 1990, Ramanujan proved Burton postulate which states that for every integer x greater than or equal to 1, there exists a prime p such that p lies between x and 2x. Prime numbers you all know, these are the numbers which are greater than 1 and it has exactly 2 divisors, 1 and itself. These are 2, 3, 5, 7, 11. But what about the Ramanujan primes? Sondo, in the year 2006, introduced Ramanujan primes. So basically, nth Ramanujan prime Rn is the smallest integer such that pi x minus pi x by 2 is greater than or equal to n for all x greater than or equal to Rn. What is pi x? This is the number of primes less than or equal to x. So if I say 8, so what is pi 8? Pi 8 is all the numbers, prime numbers which are less than or equal to 8. These are 2, 3, 5, 7. So pi of it will be 4. So this Ramanujan prime, they depend and they lie in the interval x by 2x and contains at least n primes. I will give the examples also how to find these. Every Ramanujan prime is a prime number, but the converse is not true. That every prime is prime need not be Ramanujan prime. So we say that the set of Ramanujan primes, this is always a subset of prime numbers. Ramanujan primes describe the distribution of primes in the interval x by x, and some of the prime numbers Ramanujan primes are 2, 11, 17, 29, 41, 47, etc. So how to find out this? The second prime number is 11. So R2 is 11. So the value of n is 2. So pi x minus pi x2 by x by 2 is greater than or equal to 2. How? Because we say that it is in the we are saying n is 2 and R2 is 11. So all the numbers should lie in the interval x by 2x. It's 11 by 2, it is 5.5 and this is 11. So how many primes are there in between 5.5 and 11? These are 7, 11 and 13. Okay. And this is greater than or equal to how many prime numbers are there here? These are 5, 7, 11. These are 3. Okay. But the value of n is 2. So we have this is greater than or equal to 2 as I explained. So it means this is a Ramanujan prime. Yeah, in between. It is not, sorry. So 7 and 11, this is equal to 2. And these are only 7 and 11. So let me explain with the help this why we are taking This is the least integer satisfying this condition. So if n is equal to 2, here we n is equal to 2. So the second prime, Ramanujan prime is 11. So if we find pi x, if x is equal to 11, so pi x means pi 11. How many primes are less than 11? These are 2, 3, 5, 7, 11. 5 primes are there. And if we take 11 by 2, it is 5.5. So we have, this is including 11. So we have, this is 3 in this interval. So pi minus 3 is equal to 2. So this is greater or equal to 2. If we take 13, the next prime. So up to 13, how many primes are there? These are 6. 2, 3, 5, 7, 11, 13. These are 6 prime numbers. And if you take 13 by 2, it is 6.5. So after 6.5, this is 7, 11, and 13, 3. So 6 minus 3 is equal to 3. So we can see that at least 2 primes are there in the interval x, x. Now the question arises, if I just see the next. This is the third Ramanujan prime is 70. So you can ask that why not we take 13 as the next prime number, because it is also satisfying this more than or equal to 2. If I consider 60, for example, if I consider, what about 560? How many primes are there up to 60? This is 2, 3, 5, 7, 11, and 13. So these are 6. And what about pi 8, which is 16 by 2, just pi 8. So how many primes are there? This is 2, 3, 5, 7, 4. This is 4. 6 minus 4 is 2. Before this, if you just observe, 13 has 3, but 16 has 2. So this is contradicting the statement of the or the definition of Ramanujan primes. So that is why the next prime number is 70. So similarly, when n is equal to 3, R3 is equal to 17. So we have 17, pi x is 7, pi x by 2 is 4. So this is 3. So that is why it has 3 primes in the interval x by 2 x. The sequence of prime numbers, this is strictly increasing. Its asymptotic behavior is that Ramanujan primes, these are approaching to the prime double of this, p of 2n, as n tends to infinity. The density behavior is that density decreases slowly as n increases. And we see that there are 10 Ramanujan primes below 100, 72 Ramanujan primes below 1000, and 559 below 10,000. Now comes to SSD, sum of the squares of digit. So what does it mean? Before this, I just want to explain what is junk. You know the mathematics or crossing out 9 method. So basically what we are doing, what we do, I think we have to number 817.
अब मैं वो अपने पास लेना चाहता हूँ मुझे अपने पास चाहिए.
So what we do, let we cross out 9. 8 plus 1 is 9. And we add these two numbers, 6 plus 7 is 13. 13 plus 1 plus 3 is equal to. So let us try to find the junk or digit root. If we take sum of the squares of digits, so we take the square of each digit. 8 square is 54, 1 square is 1, 49 plus 36. And we add it. And then again, we find out the sum of the square of the digits which we are getting. And then we see how many iterations are required just to get a single number. Now I am explaining you this here. If you have this number 5167, this is 312 Ramanujan prime. So you take the square of each digit, 5 square plus 1 square plus 6 square plus 7 square. This is coming out to be 111. Again, you take sum of 1 square plus 1 square plus 1 square. This is coming out to be 3. So this is 3. So terminal digit is 3. And how many iterations are required? Only 2 iterations to get this single digit sum. One more interesting thing I just, before I go for the modulus, this as a magic circle of numbers. This is 1, 2, 3, 4, 5, 6, 7, 8, and 9. We have 10, and 10 is here. But if you take the beta or the sum of this, it's 1 plus 0 is 1. Then we have 11, 1 plus 1 is 2. Then we have 12, 13, 14, 15, 16, 17, 18, 19. 19 is again 9 plus 1 is 10, which is again 1 plus 0. So you can see all the numbers they are roaming around this circle. This is known as magic circle of numbers. Now, what is the beauty of this? If you divide any number, say 10 by 9, what are you getting? Remainder as 1. And this is nothing but the cross digit sum of this. If you divide 11 by 9, the remainder is 2. And what is this? This is the cross digit sum of 11, which is 1 plus 1. If I take very large number, say 8, 1, 7, 2, 5, 4, 3. So straight away, can you say that when you divide this number by 9, what is the remainder? We can using the digit sum. 8 plus 1, 9, 7 plus 2, 9, 5 plus 9, 3. 3 is the digit. So when you divide this number by 9, and this is true for all natural numbers. So what we take that all natural numbers can be written as digit sum, which are 1 to 9. This is true for all numbers.
आवाज आपकी आ रही है वैसे
So in this way, we can say that for all natural numbers, digit root, whatever we are getting from 1 to 9, and it is true in the circle.
माइक यूज कर लीजिए ब्लैक बोर्ड पे
Recording में किया है. And so I will try to take care of this thing. So basically, we want to study the modular arithmetic of the Ramanujan prime. If we divide any Ramanujan prime by 6, we always get remainder as plus 1 or minus 1. Similarly, when we divide it by 9, you can see Rn is also digit root n modulo 9 using the same concept which I just explained. And we are taking here 10,000 Ramanujan number. Why we are taking 10,000? Because after 10,000 to 20,000, the behavior changes. As we know, prime numbers are infinite. So same way Ramanujan prime numbers are also infinite. So the procedure which I have adopted for this is that first I computed SST, sum of the square of digits. Then iterate until single digit is obtained. And then record iteration count, that how many iteration counts are required just to get a single digit root. Then computed Rn modulo 6, Rn modulo 9, and then found the relationship between the two. And I was amazed to find out. See, this is a procedure I have explained that first find SST as I took this 312. Then iterations are 2. Then modulo 6. When we divide 5 and 6, 7, this is 1. And when we take modulo 9, this is coming out to be 1. So I have prepared one table of all 10,000 numbers in this form. 10,000 prime numbers. So we can see that modulo 6 we are getting mostly -1, -1 or +1, and but modulo 9 we are getting 8, 4, 7, 5. This is the digit frequency of Ramanujan prime numbers up to 10,000. That if we take single digit 1, 85 Ramanujan primes are giving us single digit 1. 242, 7 digits are giving only 3 digit. 370, this is the most dominating number. So 370 Ramanujan numbers are giving a single digit 4. 28 Ramanujan numbers are giving 5, 6, 6. There is no Ramanujan number whose single digit is coming out to be 7. So 7 is absent. And 8 Ramanujan numbers are giving 8 single digit and 39. This is the histogram showing that 4 dominates among all Ramanujan numbers up to 10,000. This is a relationship between modulo 6 and modulo 9. That we are saying that if the Ramanujan number, when it is divided by 6, when it is given remainder 1, then the modulo 9 is given 1, 4, and 7. But whereas when you divide the Ramanujan number by 6, it is given -1 as remainder, then and you divide it by same number, divide by 9, it is giving us 258. So this is a relationship between modulo 6 and modulo 9. So when the SSD is 3, the Ramanujan model, RM number, Ramanujan prime number is 1 modulo 6, and it is also 1 modulo 9. But when SSD is 8, Ramanujan prime number is giving 1 as the remainder when it is divided by 6, and 1 as modulo 9, -1 modulo 6, but it is giving 8 when it is divided by modulo 9. This is in fact -1 also, -1 modulo 9. Similarly, when it is divided by 6, this is the relationship between modulo 6 and modulo 9. And when it is single digit 9, then this is the relationship. Digit 5, this is the relationship. And no additional restrictions arise. Rn follows standard modulo 6 and 9 constraints. So you can ask one question that why I'm taking only 6 and 9? Because when we have other modulo 2, 4, 8, 7, etc., there is no direct relationship. Among only 6 and 9, we are getting this relationship. So now we divide because I just want to go towards entropy. So I will divide this 1 to 10,000 in 10 equal intervals by defining this I as 1,000 into k minus 1 plus 1 into 10,000, 1,000 k. And we counted Ramanujan primes in each interval. So 1 to 1,000, there are 72 primes. 1,001 to 2,000, there are 63 primes. 2,001 to 3,000, 56 primes. 3,001 to 4,000, 56, and so on. In total, there are 559 primes up to from 1 to 10,000. And what we conclude from the last is that there is no major difference between the various intervals. So we can say that distribution of Ramanujan primes remains relatively stable across all the intervals. No strong clustering or large gaps observed. Dominance of terminal SSD digit 4 persists across all the intervals. Complete absence of SSD 7. There is no Ramanujan number whose SSD is 7. Pattern remains consistent globally, indicating strong structural behavior. Now with TRN, we denote this the number of SSD iterations required. As I explained in the case of 5167, we need only 2 iterations to get a single digit number. So TRN denotes the number of SSD required for a Ramanujan prime Rn reach a single digit terminal value. So we compute this. So what we observe that for SSD 1, to get SSD 1, we need an iteration 3, 4, 5, 6, 11. For SSD 2, 1, 2, 3. SSD 4, these many, because 4 was the most dominant SSD. 5, 1, 2, 3, 6, and 8. So we have different SSD terminal digits exhibit distinct iteration patterns within the same interval. And the 1 and 14, minimum 1 iteration and maximum 13 iteration. So we have this is less than or equal to 14. The number of iteration is uniformly bounded across. SSD digit 4 shows maximum variability in iteration counts. SSD digits 2, 3, 5, 6, 7, they have low iterations. And these patterns remains consistent across all the intervals, no dependence on location or size of RA. Now, next is the concept of entropy. So, in layman's language, what do you mean by entropy? It is a fundamental scientific concept that measures the degree of randomness, disorder, or uncertainty within a system. For example, if there is a messy room, everything is scattered. So, when you want to clean it, you need time and more energy. So, in this case, we say in this case, entropy is very high. But if there is a room which is just like this, everything is perfect. So here entropy is 0 or very low. Next is that if you break a glass, then what happens that everywhere you have scattered glasses, and if you just want to make form another glass from these scattered glasses, so you need energy and time also. So in that case, the entropy is very high. But if you have a perfect glass which can store water or anything else, any liquid, so obviously the entropy is very low or 0. Similarly, if we have rusting metal, iron oxidized into rust. So whenever we have a say rod of iron, it has been rusted. So there are some holes. So it is not perfect. This cannot hold the water or anything. And if you want to repair it, the iron rod, obviously you need time and energy and so many things. So entropy is high in that case. Now we come to the Ramanujan prime numbers. So I'm using here Shannon entropy. Shannon entropy of SSD distribution in IK intervals. This is defined as minus PKD log of PKD, where PKD is the probability of having this SSD. P denote the number of Ramanujan primes in the interval IK, whose terminal SSD digit is D, and terminal digits they can be from 1 to 9. So NK we take the sum of all Ramanujan numbers corresponding to different SSDs. And we define PKD, this is the probability, and probability, you know, the number of favorable cases divided by the total number of cases. So we have this is FKD divided by NK. These are the entropies of Ramanujan number in different intervals. And you can see, you can observe the maximum entropy, it is in between 1001 to 2000. And the minimum is 0.93 in the interval 8001 to 9000. So basically, Professor Kapoor also worked in optimization of entropy. This is the graph which is showing us the entropy of in various intervals of Ramanujan primes. So we can see that when HK is approximately 2.597, it gives us non-uniform distribution. And when it is 1.10, it is concentration on few, it has concentration on few digits. Stable entropy across intervals, it shows the global behavior of the Ramanujan primes. So this is the conclusion of this. Ramanujan prime exhibits strong structural behavior under SSD transformation. Dominance of terminal digit 4 and absence of digit 7 observed. There is a compatibility between modulo 6 and modulo 9. Patterns remain consistent across all intervals. Entropy analysis confirmed non-uniform and structural distribution. And this is a connection which I have done with Professor Jane Kapoor. Reflects Professor Jane Kapoor's emphasis on mathematical modeling, distribution, technical and structural analysis mathematics. The search for hidden numerical patterns aligns with this interdisciplinary approach connecting pure mathematics, system science, and theory. Exploring transformations and generalized prime structures follows Kapoor's vision of innovative mathematical methodologies and pattern-oriented research, the work continues the spirit of integrating theoretical insight with computational experimentation, a hallmark of Professor School's scholarly contribution. These are few references which I give. Thank you. And also, I want to thank the organizers, Redwall University and Vijnan Parishad of India, especially Professor Ramesh ji, for giving me this opportunity to give this keynote address. Thank you so much. Very nice. But there is no question on the end. But if you have any or questions, so you can discuss during the question.
Thank you, Professor Mathujaji, for chairing this session, and thank you, Professor Anuradha Gupta for delivering the Professor Jain Kapoor Memorial Award lecture. And thanks one and all. Now we are proceeding for the first technical session of this international conference. In this session, we have three speakers, and we have 1 hour. And after this session, there will be a lunch. We shall proceed for lunch. I request Professor R.C. Devriji to chair this technical session. And we have three speakers: Professor Satyadev, Allahabad University, Prayagraj, Professor Amit Verma. Professor Amit Verma from IIT Patna, and Professor Madhu Jain, IIT Roorkee. So I request Professor Debris to initiate this lecture. Thank you.
Thanks. So we are starting now with technical session number 1. There are 3 guest speakers. First speaker is Professor Satyadev, Head Department of Mathematics, Allahabad University, Prayagraj, and he is expertise in the field of fluid mechanics. And his topic is classification of non-Newtonian fluids and air mechanics. And over, please. There will be 20 minutes for each speaker. Because of shortage of time, there will be no again question answer session. If any, then you may discuss during the lunch session. So good afternoon to everyone. So it's a great moment for me today, because in the morning today I received the distinguished service award with the Vigyan Parishad of India, and the official members acting my name. So with thanks to all of them. So and one is the today, because I am going to present this invited lecture here. So with thanks to the organizer, especially Professor Gayola is there, and the official member of the BPI.
So we are not taking much time. We are just going to the present our the lecture. This lecture is actually divided in two parts. One part is the just we have created the classification of the non-Newtonian fluids, and then in the second part we take a problems basically based on the two research papers published recently in the 24 and 25 in the physics of fluid. So we will discuss about that problem because you know the fluid is that any object that actually has the capability of the flowing. Fluid is generally shapeless object. Some are visible and some are the invisible. They have the no shape, as you know, and some fluids are just like treated as the incompressible, whose volume doesn't change, and some fluids are the compressible, just like gases you see there, that one. You can just feel that gases, or you just smell that one, you just observing that, and their motion is a very complicated things. Because you have the name of the Newtonian fluids, and Newtonian fluid has the governing equation that is called as the Navier-Stokes equation. And Navier-Stokes equation is still $1 million problem for the mathematicians who get the three-dimensional analytical solutions. Which actually we are solving only the analytical solution, and we are talk about that advanced version of that one because I am doing the research in that area from almost 26 years. We have developed many collaborations in that area in Indo-Asian project and other from the scientists of the world. So we are just solving the analytical solution. And analytical solution are always very difficult to find the solutions. So first part is just devoted to the young researchers, those who want to do research in that area. This part is our Department of Mathematics. This Allahabad University established, as you know, this is the fourth oldest university of this India. And this part is established in 1872. And from that period, it is going on that one. And recently, this is renovated through the Archaeological Survey of India. So this part is looking very beautiful nowadays. So if you have the time, you must visit to that place. Presently, I am holding that position to that department. So I welcome to you. So this lecture is divided in that part because we have the time is very shortage, and the abstract is written here. So we are just talking about the non-Newtonian fluid because the Newtonian fluid is that one for which the stress and strain relationship is the linear one. And in those fluid in which that relationship stress and rate of strain becomes non-linear, that fluid becomes the non-Newtonian fluid. Because non-Newtonian fluid are the many applications in the field of industries, food process and other membrane filtration technique is there, and the oil filtration technique. So we are doing about that one for the non-Newtonian fluids. So these are some example of the non-Newtonian fluids, and you see here. One is the rheopectic fluids, and another one is the shear thickening fluid. Shear thickening fluid is that one when which you apply the shear, you apply the force, that one, they will become thicker. So that viscosity will increase it. And some other shear thinning fluid is there, just like paint is there, you apply that one, that will become a very thinner. Yeah, just ketchup is there, if you stir the bottle, and that fluid will become a easier to flow that one. And in the real world application is there, the oil rigging, that is and in the oil filtration. So and the body armor also use the this non-Newtonian fluid because this non-Newtonian fluid is the light one and they are the protected. So if you apply the shear thickening fluid, suppose blade hit the this body armor and that shear thickening fluid will become a thicker one, then that shock will absorb in that body armor. So classification of non-Newtonian fluid. Non-Newtonian fluid is based on their predominant physical property. So we have basically the three types of the non-Newtonian fluid. One is the time independent fluids, one is the time dependent fluid, and another one is the viscoelastic fluids. Time independent fluid in which the non-Newtonian fluid in which the shear rate and strain rate depends on the time. So they are basically divided in the two categories. One is the purely viscous fluid, another one is the viscous fluid. A purely viscous fluid is that one in which the constitutive relation is written in that form. Shear stress is simply related with the rate of strain, and the coefficient mu comma dot is written here. This is their apparent viscosity, and this apparent viscosity plays that role to divide the fluid in the different parts. So their shear thickening fluid are again divided in the two parts. Shear thickening fluid is that one in which the apparent viscosity decreases with increasing the shear rate. If you apply the shear rate, the viscosity increases. The term pseudoplastic is also used for that one, for shear thickening fluids, because it appears like plastic-like behavior. So easier flow when stress is applied, polymer melts, polymer solutions, biological fluids, they are coming in that category. And shear thickening fluids don't have any yield stress, but they, when you apply that stress, then they have the capability to flow. Shear thickening fluids. Shear thickening fluids are those fluids in which apparent viscosity increases with increasing shear rate. So shear thickening fluid are termed dilute fluid because their volume increases when you apply the shear rate. Some well-known example of shear thickening fluids are the corn starch suspension, silica suspension, pea sand, etc. There are the several mathematicians model because still we have the problem that analytical solutions. So different mathematical model developed to solve the non-Newtonian fluid. Some of there is the power law fluid, cross fluid, Cisco fluid, Prandtl, Eiring power model. Different mathematicians have the different models. Depends on simply that one. There you simply write the shear stress and the rate of stress relationship. If you write the relationship in that one and then you apply that technique to solve that one, so that will become the problem related to that fluid, and that got the name of that mathematician that will initiate that things. Because we have initiated recently this topic, so we are just introducing the things. So viscoplastic fluids. Viscoplastic is a class of time independent non-Newtonian fluid that behave like a solid until we apply the yield stress. So these toothpaste, as you know, you apply that yield stress, they have the capability of the flow, mud, chocolate, molten, etc. So they are again have the different viscoelastic model. One is the Bingham plastic, Huxley, Berkeley, and Kesan, etc. So this is one of the graphical representation of these non-Newtonian fluid. Newtonian fluid is that one in which the shear stress and the that simply green line is there. That relationship is simply linear one. And pseudoplastic fluid is that in which some nature is different type and the dilute fluid in the volume increases. Here is that just like water is Newtonian, and then we have some yield stress. The yield stress is there in that category is the Bingham fluid, Huxley, Berkeley. So that fluids are coming in that category. Time dependent fluids. Time dependent fluids are those fluids in which the apparent viscosity changes with time under a constant applied shear stress and strain rate. So different fluid has a different behavior. You don't have to simply say if fluid has simply one behavior. So in that category, that is the thixotropic fluids, viscosity decreases with time, and rheopectic fluids, viscosity increases with the time. So thixotropic fluids are that fluids just like paint, spring muds, printing inks have time dependent shear thinning property. So they are called as the thixotropic fluids. And rheopectic fluids are that one, gypsum, paste, polymer suspension, and lubricants. So they are coming in that category. So these are again the graphical behavior of these this Newtonian fluid, pseudoplastic, dilute, volume increases, thixotropic, Bingham plastic, and rheo. And the yield stress is there. When you apply that yield stress, they behave like a fluid structure. The viscoelastic fluids. Viscoelastic fluids are those exhibited dual behavior, viscous as a liquid, and then become elastic as a solid. So when subjected to a deformation. So viscoplastic elastic fluids are that one, just like mucus, gel, toothpaste, etc. coming in that category. And then further we are divided the microstructural fluid. So microstructural fluid is that one in which the fluid particle dissolve. They have some rotational tendency. When we have the rotational tendency, and this is in the category of that micro level, this particle they have the size 10 to the power minus 6 meter. So they have the rotational tendency, and the fluid also we have just like in the same way. So we have the micropolar fluid, couple stress fluid, polar fluid. So different fluid in that category is there because we are taking one problem here, and that is simply based on the couple stress fluid. They have also the same nature. So couple stress fluid. Couple stress fluid is that one Because that relationship simply the number 2 is written, Tij is equal to this one. That relationship is simply Ij is 1 to 3. So these are the 9 relationships here. As far as simply Newtonian fluid, they also have the name relationship, but simply these are a linear relationship, and the problem will become $1 million. Here the problem will become above than the $1 million if you get the analytical solutions. So we have the solutions in the different situations. In this simple geometry is easier, just like quasi flow, quad flow. If you two plates is there, one four plate are the rest, or some pressure gradient is there. So such type of fluid can be solved by doing their modeling and using their constitutive relationship. Constitutive relationship is the main foundation of the fluid nature. So we have this relationship here because we are doing one problem. So that dynamics of non-Newtonian fluid is simply based on the conservation of mass. Just like in the classical mechanics, we have no conservation of mass principle there, because in the solid object mass is always conserved. In the case of fluid, that mass conservation that reflects in the form of equation of continuity. If that equation of continuity doesn't hold, the fluid motion isn't possible. So here the conservation of mass should be there, and the linear momentum conservation and constitutive relationship. And if you are doing the energy problem, the energy conservation will be also that law should be included, because we are simply doing here the flow problems. So we are basically applying the three laws. One is the conservation of mass, one is the conservation of linear momentum, and another one is the constitutive relationship. And if you have the rotational problem, you should have a rotational equation for that one. So that should be conservation of angular momentum. So this general momentum equation is simply written here. This is the left side part is written here. This is the total inertia part. First part is simply del V by del T. This part is the local convective part, and this V dot del V part that will create the problem non-linearity, and that non-linearity related to the $1 million. So this V dot del V part will be complicated part to solve the problem. And then the pressure gradient is there, and the stress and their divergence of the stress will be there. So that should be also a vector quantity, because this vector is left hand side, so right side should be also a vector thing. So we are doing this problem in the second part. This problem is published in the Physics of Fluid, Operator Journal of the Physics, Fluid Mechanics. So this we are doing this problem based on simply two papers published in the Physics of Fluid. In simple problem is there. Problem is there. Once a sphere is put in here, either we take the solid sphere or we take the porous sphere. In one problem we have taken the solid sphere. In another problem we have taken the porous sphere. So that's a good generalization of that one. And that porous sphere is implanted in a porous medium, and is porous medium flow of a couple stress fluid. The couple stress fluid is flowing, and simply a sphere is put in that medium. And if you put either two, three different size of spheres, that problem will become complicated. And we are solving such type of problem with the membrane filtration. So that problem we are not simply a simple sphere is there. Either we are taking a solid one or we take a porous one. And the couple stress fluid is here. And couple stress fluid for that constitutive relationship is written. I say 1 to 3. So these are the 9 equations for the constitutive relationship. And then we put in the Gauss equations, that will become the 3 equations by the momentum. So these are the basically equations written in the form of that.
methods, NSFT, right? What happens in this? Suppose you have, say, y dash, you want to discretize finite difference, so what do? You just replace this by its this formula, right? So this is called finite difference. This is for non-standard finite difference. What happens? Here you replace this h by sin h, for example. Then, and here this, you have written here, say 1 is written here, coefficient 1. You can replace so by some function phi h, which goes to 1, which like as h tends to 0, right? And you can see that this is same as h when h tends to 0, actually. So this process is called non-standard. This is called non-standard finite difference. So it is given by RE Mechanis, right? So I'll not go into detail of this. If anyone is interested, he can write to me. I'll share some books. 2 books are there, 2-3 books and some papers. You can start learning this non-standard finite difference methods. So with Dr. Lacha, I worked on adjustable finite difference method. With Dr. Srini, my PhD student, I worked on her thesis is on non-standard finite difference methods. Then Mukesh, he actually coupled Haar wavelets and NSFT, and he solved PDEs actually. So like for example, if you take heat equation, so on with respect to x variable, he used Haar wavelets, and with respect to time variable, he used NSFT. It's a coupling both methods. So his thesis is on NSFT plus Haar. Then currently Bhavika she worked with me for 2 years. Then currently she is working in Germany. She is also writing a paper on non-standard finite difference method. So this is the acknowledgement section, and this is the way. So basically, today's I'll be discussing about adjustable methods. NSFT I will not talk about much, but you can start this RE with an idea. I've given the idea what is called NSFT, and you can read these papers and books. You can have very easy to learn, difficult to implement. Okay. It's not moving, not going to next slide. Shall I scroll? Okay. Acha. Okay, fine.
Yes, so this it.
वो नहीं काम कर रहा है.
So 2 fingers.
2 fingers. Okay. मुश्किल है भाई. You open it with PDF. Open with PDF. Escape. Escape. Close it. Close it.
Yes.
Where is the file? Here. Right. Right click. Open with PDF है कि नहीं है? नहीं है ना?
सर ये Microsoft Edge.
नहीं उसे खुलेगा?
हाँ सर खुलेगा.
तो ऐसे ही चलेगा फिर. फुल स्क्रीन मत करो तो आई थिंक काम करेगा. ठीक है. We shall not do full screen. Then it will work. Fine. Leave it. Not required. Fine.
आपकी सारी होगी.
हाँ. So basically I start with mentioning few lines about Professor Aman Chawla. So basically, this is the paper which I read during my PhD, and later when I started working on unstable methods, I saw some papers written by Professor Chawla in this area too. So basically, he's no more, but so I have some very interesting biography. So he did his BSc from University of Delhi, and then he became faculty first. Then he completed his PhD later from. So he joined IT in 1963 and he did his PhD degree later. And he was at Kuwait, he was head also. So this picture I got from Professor Meena Samet. She is currently HOD of Lucknow University. And she basically, her colleagues did PhD with Professor Chawla. So this picture she got for me, she got it from the students of Professor Chawla. So basically, his work actually motivated us to work in this area. These 3 formulas is well known to all of you. Trapezoidal rule, Simpson's rule, right? They seems very simple, but you can use them to solve, say, heat equation or complicated some non-linear PDs also you can solve by using these. For example, suppose you want to solve this equation, right?
by with say y t naught equals to y naught. This initial condition is given. You are suppose you want to use trapezoidal rule. So what you are supposed to do? Just integrate it from x naught to t naught to t. So you'll be getting maybe y t naught t. And then here you'll be getting t naught to t f t y dt. Now this integral you can solve by using trapezoidal rule. Very simple, right? So, but there are several issues with these methods when you try to apply it on, say, especially stiff differential equation. If stiff differential equations, they have solutions which very slow in certain domain of time, and in certain domain they very quick, rapid changes there. So numerical methods should be there so that they can capture solutions for any time. So these methods, if you try to apply on stiff differential equations, they will not give solutions, very reliable solutions, right? So before I further go ahead, because you can see that if you solve this equation, you can easily solve this PD also. The basic idea is that say on say with respect to x variable, you apply some finite difference, and then with respect to time you integrate it. So with respect to x variable, you apply finite difference. So you will get a system of equations. And then on that system of equations, you integrate by using this formula. You can solve this, right? So that is why we have taken this problem. And for testing various stability issues, this equation is used, which is called actually test equation, y dash equals to lambda y. Where lambda can be complex also. Why lambda can be complex? Because when you deal with system of equations, system of differential equations, then you arrive at matrices. This lambda will be replaced by some matrix. So matrix can have complex eigenvalues also. That is why lambda is allowed to be complex when we deal with the when we test the numerical methods, right? So if you this is a very simple differential equation, all of you know the solution. It is in this form, and if real part of lambda is less than 0, then solution increase. Now, if you apply any one-step numerical method, then you will get this kind of iteration. Now, when t increases, you can see that for real part of lambda, y will decrease. So, if the numerical method is stable, then this yn plus n solution at y at tn plus 1, yn solution at y at tn. So, solution decreases 1 shall happen. This modulus of this should be less than 1. Then only at every iteration your solution will decrease, right? So this is used to define stability. So numerical method is said to be astable if you can express the method like this. Then if mod of phi z is less than equal to z for all z, the real part of z less than equal to lambda. That means for all negative complex numbers, left half the complex number, phi z should be less than equal to 1. That means region of stability is entire left half complex plane. Then your method is astable. Then a method is astable if it is L-stable as well as it satisfies this condition also. So for stiff differential equation, at least your method should be astable and it should be L-stable if you want further better results, accuracy. Now there are some simple well-known methods, forward diagonal, backward diagonal, they are well known. You can see that forward diagonal is not at all astable, right? So it cannot be L-stable. It is astable as well as L-stable. Trapezoidal is astable, but it is not L-stable. So when it comes to stiff differential equations, even trapezoidal rule does not give you very good results. So in this respect, regarding stability, Dahlquist, he wrote 2 papers, very important papers, and one of the conclusion of the paper is no linear multi-step method of order greater than 2 can be stable. That means if your order of accuracy is greater than 2, then the method will not be stable. So if you increase accuracy, it cannot be stable, but it is very good for stiff differential equation. So people try to increase the accuracy and as well as they try to get stability also. So this is the basic idea which leads to this today's talks, ideas and papers that I'm going to discuss. Right. For example, this is there are some results earlier, but this is a basic paper. Ravi P. Agrawal is a very famous Indian mathematician who was in US. He recently died in India somewhere in Rajasthan. So he, along with Usmani, they wrote a paper and they increased the accuracy of trapezoidal rule. Right? They increased the accuracy of trapezoidal rule. This is the paper. Right? They gave stable extended trapezoidal rule for integration of ordinary differential equations. So the basic idea is, see, suppose alpha 2 is 0. So this is nothing but the trapezoidal rule. You read this Z as Y. This is a typo. So if alpha 2 is 0, this is nothing but the trapezoidal rule, provided alpha, if you pick alpha not half, alpha not half, then it is trapezoidal rule. So what they did? They added this term. Right? Now this is a multi-step method. Right? But they again define this this value, Zn plus 2 value, by this term, another term. So if you see this combined formula, this is not a multi-step method. This is a single step method, because finally, if you put this value here, only n plus 1 will be depending on nth value. Right? So by this trick, they bypass the statement of Dahlquist. So Dahlquist result is no longer applicable on this. And by this, they have shown that this method is of order this convergent, which is higher than trapezoidal rule, and it is astable, but it was not unstable, right? So later he extended this further. Idea is same. Again, he took the same thing, did some manipulations, but in the earlier case, beta naught was fixed. It was not so, but they have chosen the parameters in such a way that they have more number of parameters, less number of equations. So one parameter is free, so you can choose it. So you have a family of equations, and for beta naught equals to 1, the method is not only astable but unstable also. So he derived the same thing, but again his method is unstable also in this process. Now, in this paper, this author and with some other author, the earlier author with some other author, what they said, if you wish to increase the accuracy further, means you wish to go to say 4th order, then this trick will not work. He said, then you have to add one more term, and then you have to assume that this Zn plus 3 can be written in terms of other function values. Okay, and then he increased the accuracy also by claiming that the previous technique that adding one term, by adding one term, you cannot increase the accuracy. They claimed it. Now here, so here comes the work of Professor Chawla, who is from IIT Delhi. What he said, no, it is possible to do it without adding an extra term, and he's shown it in the paper. Right. So this term is there, but they both, he assumed that Zn plus 2 and Zn plus 3 both are written in n and n plus 1. So basically in the previous one, they have 3 indices. Finally, in this assumption, they have only 2, n plus 1 and n. So this is a very crucial result, and they increase the order to 4th, right? Then in another paper, he said that by this process, you can go up to maximum of order 5. Beyond that, you cannot increase accuracy, right? I skipped some papers. I will come to this paper. So in this paper, this is a basic paper which motivated us to do our work, which we did. So in this paper, he used Simpson's 1/3 rule. Which rule? Simpson's 1/3 rule. Simpson's 1/3 rule is order square 4 convergent globally. But if he introduced L stability in the Simpson's 1/3 formula, and he has shown some solutions of nonlinear PDEs, right? So once you introduce L stability, the order reduces by 1. Simpson's 1/3 is S power 4 convergent globally. But if you introduce L stability order reduces by 1, third order. But what he has shown that Craig-Nicolson scheme can produce unacceptable oscillations, but his method does not produce any oscillations, right? Craig-Nicolson is a very popular method. So this paper motivated us to learn this technique actually, and this is our paper. We did it for Simpson 3/8, published in Applied Mathematics and Computation, and here I have shown that you can see the for very small nudies, coefficient of viscosity is in Burger's equation. You are getting very good solutions. Accuracy profile is maintained. Here, in case of, you can see the Craig-Nicolson is oscillating, but our solution is matching. So this is the first work in this direction we did. Right. Then we further we try to increase accuracy further. Right. So we use polynomial of degree 4. Simpson's 3/8 uses polynomial of degree 3. So we use polynomial of degree 4. That is called Boole's rule. And we extended the method, but there's a problem that our formula is not perfectly astable because its region of stability is not entire left half plane. There are some singular points added on the right also. So this is the trouble. But still, it satisfies the condition of L stability. That is why, like we refer this formula weakly L stable formula in this paper, right? And we further extended the accuracy and published in 2021. See, weakly L stable we are using. And here I have, clubbed non-standard also with this technique. So non-standard, it was here, right? I clubbed it with L stability, and we published the paper. Further, we increase the accuracy to any. So this is a recent paper, 2024. This is for any order. We have given a general formula. You change the polynomial, you get a formula, and then procedure is given. So this is all. With this I stop. There are nothing, but I'm just.
Thank you, Professor Verma, for giving this motivational lecture. And really for me also, there are the new concepts like NSFD and HAR methods. Yes. So because of shortage of time, you could not finish your talk. And now I would like to invite Professor Madhu Jain from IIT Roorkee on the software reliability models and statistical machine learning.
Presentation. Slides start. Mike. Follow Mike. Hello. Hello. Good afternoon, all of you. I am thankful to the authority of the PPI as well as the organizer of the conference for inviting me to deliver this talk. Time is very less. I will try to complete in 15 to 20 minutes, of course. So here I am discussing the topic that is the software reliability growth models. We have developed many models by taking a non-homogeneous Poisson process and using the distribution, single distribution. So today we are discussing the multiple distribution, hybrid distribution we are using for the prediction of the software reliability. And because there are one method in the machine learning based on the distribution, that is the GMM, Gaussian mixture model they are using. So we try to extend the work of the Gaussian mixture model to take the different type of the distribution and its application to software reliability. So first, we model are the non-homogeneous Poisson models are the stochastic models, and the stochastic models are more realistic in comparison to deterministic models. And we are using the distribution, various kind of the distribution, so that we will also discuss. When we are taking a distribution, we are using the PDF, probability density function, and the cumulative distribution function. To take the indices, statistical indices, we are taking the expectation about the zero. That first expectation that gives to the mean, and the expectation about the mean, second gives you the variance, and other indices are also important. Mainly these two indices are common when we are doing the performance modeling. So what is the software reliability? Actually, we are taking the probability of the failure-free software subject to some specified condition and for the given interval. So there is a little bit difference between the hardware and software reliability. In software reliability, we are also concerned about the environment, in which environment software is working, so that we are taking into consideration. So whatever model we are developing, that is used to increase the software reliability, of course, to predict the hello, of course, to predict the testing time. So whenever we are taking the development of the software, a lot of time are spent on the testing. So at some point of time, we have to release the software. So what is the upfront testing time? And that we are going to discuss here. So software reliability has the mainly three aspects. We want to reduce the bugs, means errors in the software, and we reduce the downtime of the software, because no software is the 100% reliable. At some point of time and due to some reason may fail. So we want to reduce the downtime of the software and reduce the bugs time, because there is a lot of testing is done. So to fix the bugs, the time should be less. So that's why we are doing the software reliability. So whenever we are taking the development of software, a lot of testing are done during the requirement phase, coding phase, then testing phase, and even after testing, it is launched into the market. There is the testing of the software in the operation phase. So a lot of time, even 60% of the development time is spent on the testing of the software. So very important topic, because in the starting in 79, many product phase, and even NASA has some project that phase due to software reliability software. So they have introduced the branch of the software engineering, and the work started in the 1979 on the software reliability. So we are using here the machine learning. Actually, I am taking the course of the statistical machine learning. So earlier, whatever existing literature is based on the reliability models on the non-homogeneous Poisson process by using the single distribution. But by taking the mixture distribution, we can predict the more realistic situation. Whatever data is available in the, we take those data and fitting the models. And whenever we are fitting the mixture model, it gives the better results in terms of the statistical indices. So that we are taking into consideration. So there are many distribution. Generally, people are taking the exponential distribution. Starting models are there, but we have to take the more advanced distribution. So here we take the Wavell distribution. It take the both type of the density function. So for increasing and decreasing failure rate, it works well. And gamma distribution. So for the gamma and Wavell distribution, we have the probability density function, mean time to failure, and mean time to and reliability also. So we'll consider. So these are the distribution function we have taken. Log normal distribution is also used, and Frechet distribution. So in mixture model, whatever we are taking the linear combination of the distribution by associated with the some weights. So basic models of the mixture models are based on the fixed weights, but we take the more advanced way, that is by taking the weights are also distributed according to some distribution. So that kind of things are introduced. So this kind of work is not available into the literature, but we have tried to find out the dynamic weights for the mixture models and predicting the software reliability and the failure time of those software. So whenever we are taking the distribution, so we have the Weyl exponential gamma. So here mean time to failure we can calculate based on the theory. And reliability is, in general, you can say that this is the complement of the failure distribution. So those functions are given here. Hazard rates, we are also calculating for the different distributions. So this is tabulated here for some distribution. So whenever we are taking the statistical indices, whatever modeling we are doing, we are interested in the mean absolute error, mean absolute percentage error, root mean square error. And in case of the machine learning, we are taking the more indices to check the goodness of the fit of the models. AIC and BIC is also used to check the goodness of the fit of the model. So whenever so we take the mixture distribution as a linear combination of the distribution. So here you can see the mixture distribution, and theta i's denote the parameters. So whenever we are fitting the mixture distribution, we have to estimate the parameters, and Wn is the weight associated with each distribution, and sum of the weights should be equal to 1. So in the literature, we are having the Gaussian mixture model. GMM is very well used in the machine learning. So GMM is the combination of a normal distribution, that is called the Gaussian distribution. So for fitting of the real-time distribution, we are taking the multivariate distribution. So in Python, we have the ready-made program for this one and fitting the data based on this one. So what is the use of the picture distribution? It gives the more realistic picture of the model. So we have for the survival analysis, say in case of the software system, we are having the survival analysis, lifetime of the software, we are using this model. So for the multivariate distribution, Gaussian distribution is given in the last row. This is the in terms of the covariance and the mean of the distribution. So for multivariate distribution, we have this kind of the cumulative distribution function. So if we are taking the hybrid distribution, 3 distributions we are taking in the first slide picture, and the second blue lines, blue curves gives you the picture of the 3 distribution. Actually, in case of the corona, we are also having the different peaks. So for the different peaks, we are taking a different distribution, then combining that one to generate the mixture distribution. So whenever we are taking the fitting of the curve or fitting of the model, we need the parameter estimation. So for the parameter estimation, in machine learning, 2 methods are popular. That is the maximum likelihood method, that is very common in the statics. And second method is the maximum method is also there. So we shall use that one. So expected maximization algorithms can be used for the parameter estimation. So it is based on the 2 steps. First step is that we calculate the expectation. In the second step, we iterate to generate the mean, covariance, and the mixing weights. So based on the GM model, we have the classification of the data, and this is done based on the Python program. So Python program for GMM is also given here. We are not taking much detail for that one. But for the dynamic weights, we are taking the mixture of the different distribution. Here we take the 2 distribution, stable and non-normal, by taking the dynamic weights. Dynamic weights means weights we are having the Poisson in this case, and other ways can be used. We have the different models by taking the picture of the distribution, then we are fitting the data and we will check based on the indices which one is the best model. So reliability indices calculated for these dynamic picture models. Other indices are also there. So Poisson dynamic picture model of the Webel and log normal probability density function is formulated. Here where the weights are the Poisson distributed. So reliability function can also calculate it based on the formula. Those who are familiar with the reliability can easily get this one. And hazard rate is also important for that one. So whenever we are taking the goodness of fit data, here we take the data of the supercomputer, that is a blue supercomputer of the California University. We collect the failure data, then we are fitting the parameters based on the both log likelihood function, and we are taking the maximum likelihood method as well as the EM method for that one. So two indices are important to check the accuracy of the model, that is the AIC and BIC given here in this formula. So whatever model mixture, we are taking here the mixture model, single model are available in the literature, but for the software reliability, nobody has used the mixture model. Even weightage, dynamic weights are not used in the literature for the reliability prediction. So we are taking the combination, then whatever data we have collected for the supercomputer. So based on, we take the parameter estimation based on the EM method as well as the log likelihood method. So this is the values given there. And indices AIC and BIC are calculated. Based on AIC, BIC, we decide which model gives you the better fitting of the curve. So other combination of the distribution and the parameter estimation are given here. So for the dynamic picture, whatever data is available for the supercomputer, and we have tested this not only for the software reliability, for the others real life data, we have tested the distribution. So these are the parameter estimation values. So whatever model we are discussing here, that is based on the continuous models, that is the non-homogeneous Poisson process method. So non-homogeneous Poisson methods are largely used in the software reliability. But what is the objective here? We have to use the mixture model and compare the single model. And not only we take the single model, we take the many models, double the many models, and based on the indices AIC, BIC, and other indices, we check which model is the best fitted to the curves to predict the failure of the software. So this kind of the work we are doing here. So I am not discussing how we take the development of the model, just whatever I have presented, real-time data we are taking and taking the different picture models, and then parameter estimation is done. And then those mixtures model we are checking which one is the better fitting of the data. And then we predict the future forecasting of the failure of the results. And even for the classification and the clustering, we are using this model. And because in the machine learning, statistical machine learning, it is a bit more cumbersome. So people are not using the distribution, but it is a very important area because real-time system we are having. So we have to put the advanced model and check whatever existing models. In the starting for the software reliability, they have the model based on the single distribution, exponential distribution, then SCM model and so on. But that is for the advanced system, there is the hybrid model, embedded system. So those will not work well. So mixture model can be tested, and once we are testing the model, which one is better, so we can use in the real life situation. So that's all I want to present.
Okay, thank you. Now, please.
Thank you, Professor Silendriji, for conducting this first technical session. Now, I request organizers for the certificates and memento to the respected speakers. May I request Professor Satyadev ji?
Huh?